Imagine standing on a windswept beach, the vast ocean stretching out before you, seemingly endless. Now replace that ocean with the cosmos, speckled with billions upon billions of stars. The question that has haunted humanity for millennia arises. Does it ever end? Is there a cosmic shoreline, a boundary to existence itself? This isn't just a question for physicists and astronomers. It's a primal yearning to understand our place in the grand scheme of things, a quest that has driven philosophers, poets, and dreamers for centuries. Think back to the ancient Greeks, meticulously mapping the stars, attempting to define the edges of their known world. They imagined celestial spheres, concentric shells containing the sun, moon, and stars, all revolving around a central Earth. But what lay beyond those spheres? Was it chaos, void, or something completely unimaginable? The concept of infinity was, and remains, a truly mind-bending idea. For generations, we have pointed our telescopes towards the inky blackness, each new observation only deepening the mystery. Every galaxy we discover, every nebula painted across the sky, seems to push the boundaries further and further outward. Are we simply seeing more and more of an infinite expanse, or are we catching glimpses of a truly finite universe, one that, despite its staggering size, has an ultimate limit? Consider the sheer audacity of this question. We, tiny beings on a small planet, daring to ask about the fundamental nature of reality. It's a testament to the human spirit, this relentless curiosity that drives us to explore the unknown, even when the answers seem impossibly out of reach. But what if there is an edge? What would it look like? Would it be a wall of fire, a shimmering curtain, or something so alien that our minds simply couldn't comprehend it? Or perhaps, even more unsettling, would it be nothing at all? A gradual fading into what? This isn't just abstract speculation. The answer to this question has profound implications for our understanding of physics, cosmology, and even our place in the universe. It challenges our very perception of reality. Are we living in a vast, ever-expanding cosmos with no end in sight? Or are we confined to a cosmic bubble, unaware of the true scale of existence? The journey to unravel this enigma is one of the greatest intellectual adventures humanity has ever undertaken, and it begins with a simple yet profound question. How far does it truly go? Prepare yourself, because everything you thought you knew about reality is about to be challenged, and so we stand at the edge of the known, peering into the abyss. But what if that abyss has a limit? A cosmic boundary beyond which our telescopes, our most sophisticated instruments, simply cannot penetrate. It's a tantalizing thought, both liberating and deeply frustrating. Liberating because it suggests a definable scale to our universe, something we can, at least in theory, comprehend. Frustrating because that very limit might forever prevent us from grasping the true extent of reality. Think of it as standing on the shore of a vast ocean, believing it stretches on forever. Then, someone points out that your vision is limited by the curvature of the Earth. You can only see so far. Beyond that horizon lies more ocean, but it's hidden from your view. That, in essence, is the concept of the observable universe. This cosmic bubble, as it's often called, is a sphere of space approximately 93 billion light-years across. That's 93 followed by 9 zeros, light-years. A distance so vast it dwarfs human comprehension. It represents the portion of the universe from which light has had time to reach us since the Big Bang, roughly 13.8 billion years ago. Remember, light, despite its incredible speed, isn't instantaneous. It takes time for light from distant galaxies to traverse the immense gulfs of space and finally reach our waiting telescopes here on Earth. So everything we see, everything we can detect, lies within this 93 billion light-year sphere. But what defines that boundary? It isn't a physical wall or some kind of cosmic barrier. It's simply the limit of what we can see, dictated by the age of the universe and the speed of light. Imagine a single firefly blinking its light in the night. If you're close enough, you'll see its flash immediately. But if you're incredibly far away, that light might take a long time to reach you, perhaps even longer than you're alive. Similarly, there could be galaxies out there, even more distant than the ones we currently observe, whose light hasn't yet had time to reach us. They exist, they're out there, but they are effectively invisible to us, hidden behind this cosmic curtain. This limitation applies to all forms of electromagnetic radiation, not just visible light. Radio waves, X-rays, gamma rays, all are bound by the same cosmic speed limit. This means that even our most powerful radio telescopes, capable of detecting faint signals from the earliest moments of the universe, are still constrained by this fundamental barrier. Now, it's crucial to understand that this observable limit isn't some kind of fixed boundary. It's constantly expanding. As time passes, light from ever more distant objects has the opportunity to reach us, gradually increasing the size of our observable universe. It's like the tide coming in, slowly revealing more and more of the seabed. But even with this constant expansion, the question remains: what lies just beyond this cosmic curtain? What wonders, or perhaps horrors, are hidden from our view? Is it simply more of the same, an endless expanse of galaxies and stars, or something fundamentally different, something that challenges our understanding of physics itself? This cosmic horizon, this boundary to our knowledge, is not merely a physical limitation. It's a philosophical challenge. It forces us to confront the possibility that we may never know the true extent of reality, that there may be regions of the universe forever beyond our reach, their secrets forever locked away. But perhaps, just perhaps, there are ways to indirectly infer what lies beyond, to glean clues from the faint echoes of the Big Bang, or from the subtle distortions in the fabric of space-time itself. Perhaps the key lies not in what we can see, but in what we can infer. And what if our observable bubble is but one of countless others, floating in a vast, unknowable multiverse? But how can we even begin to fathom what lies beyond that horizon? Is there a cosmic Rosetta Stone, a key to unlocking the secrets of the unseen universe? The answer, surprisingly, may lie in the faintest whispers of the early cosmos, a ghostly afterglow that permeates all of space. It's a relic of the Big Bang itself, a cosmic fossil known as the cosmic microwave background, or CMB. Imagine holding a photograph taken just 380,000 years after the universe was born. That's the CMB. 380,000 years might seem like an eternity, but consider that the universe is roughly 13.8 billion years old. That 380,000 years is less than 0.03% of the universe's total age. Infancy, indeed. Before this time, the universe was a seething, opaque plasma of protons, neutrons, and electrons, so hot and dense that light couldn't travel freely. It was a cosmic fog, an impenetrable curtain obscuring the universe's earliest moments. Then, as the universe expanded and cooled, these particles combined to form neutral atoms, primarily hydrogen and helium. Suddenly, the cosmos became transparent, and light could finally stream across the vast distances of space. This ancient light, stretched and cooled by the universe's expansion, is what we now observe as the CMB. Think of it like this. Imagine a blacksmith forging a sword. The metal glows white-hot, radiating intense heat and light. As the sword cools, the glow fades, shifting from white to orange to red, until finally it radiates only infrared light, invisible to the naked eye. The CMB is like that afterglow, the faint heat signature of the Big Bang cooled and stretched across billions of years. But why is this ancient light so important? Because it provides us with a snapshot of the universe in its infancy, a glimpse into the conditions that existed just moments after creation. It's a treasure trove of information about the universe's age, composition, and geometry, and perhaps most importantly, it hints at the existence of something far larger than our observable universe. The CMB was first detected in 1965 by two radio astronomers, Arno Penzias and Robert Wilson, who were working at Bell Telephone Laboratories. They were trying to calibrate a sensitive microwave antenna, but they kept detecting a persistent uniform background noise that they couldn't explain. No matter where they pointed their antenna, the signal remained the same. Initially, they suspected it was a problem with their equipment, perhaps even pigeon droppings interfering with the signal. It took them some time to realize that they had stumbled upon one of the most important discoveries in the history of cosmology. A discovery that would earn them the Nobel Prize in Physics. What's truly remarkable about the CMB is its incredible uniformity. It's almost perfectly uniform across the entire sky, with temperature variations of only a few parts in 100,000. Imagine a perfectly smooth lake, disturbed only by the tiniest ripples. That's the CMB. This uniformity presents a puzzle. How could the universe have been so uniform in its early stages, when different regions were so far apart that they couldn't have possibly interacted with each other? This is known as the horizon problem, and it's one of the biggest challenges facing cosmologists today. The leading explanation for the CMB's uniformity is a theory called inflation. Inflation proposes that in the first fraction of a second after the Big Bang, the universe underwent a period of extremely rapid expansion, faster than the speed of light. This exponential growth stretched out any initial irregularities, smoothing out the universe and making it remarkably uniform. If inflation is correct, it has profound implications for the size of the universe. It suggests that our observable universe is just a tiny patch within a much larger, possibly infinite, cosmos. Think of it like this. Imagine blowing up a balloon. As the balloon expands, the surface becomes smoother and smoother. If you were a tiny ant living on the surface of the balloon, you might think that the balloon was infinitely large, even though it's actually finite. Similarly, our observable universe might appear to be smooth and uniform, even though it's just a small part of a much larger, possibly infinite reality. But does the CMB really hold the key to infinity? The answer is complex. The CMB's uniformity is certainly suggestive, but it's not definitive proof. There are other possible explanations, and the debate among cosmologists continues. But as we continue to study the CMB with ever more sophisticated instruments, we may uncover new clues about the universe's true size and shape. Perhaps within those subtle temperature fluctuations, those tiny ripples in the cosmic afterglow, lies the answer to the ultimate question: is the universe endless? Or does a boundary exist hidden just beyond our sight, a boundary that may forever remain beyond our grasp? The search continues, driven by our insatiable curiosity and our relentless pursuit of knowledge. What secrets will the echoes of creation reveal next? Even with the secrets whispered on the cosmic microwave background, a burning question remains. How can we truly know the distance to these ancient signals, to the galaxies scattered across the observable universe, to even begin to paint a three-dimensional map of existence itself? The answer lies in a set of ingenious techniques, cosmic yardsticks, if you will, that allow astronomers to measure distances that dwarf human comprehension. Think about trying to measure the height of a towering redwood tree. You could climb to the top with a measuring tape, a daunting and potentially dangerous task. Or you could stand back and use trigonometry, measuring the angle to the top of the tree and the distance to its base. With a little math, you can accurately determine its height without ever leaving the ground. Astronomers face a similar challenge, but on a cosmic scale. They cannot simply travel to distant galaxies with a measuring tape. Instead, they must rely on indirect methods, on clever observations, and the immutable laws of physics. One of the most important of these cosmic yardsticks is something called a standard candle. Imagine a lighthouse, its beam shining with a known intensity. If you see that lighthouse from afar, you can estimate its distance based on how bright it appears. The dimmer the light, the farther away the lighthouse. Certain types of stars behave in a similar way, acting as cosmic lighthouses that allow astronomers to measure vast distances. Perhaps the most famous standard candles are Type 1a supernovas. These are the explosive deaths of white dwarf stars, the remnants of sun-like stars that have exhausted their nuclear fuel. Under specific conditions, a white dwarf can accrete matter from a companion star, eventually reaching a critical mass. At that point, it undergoes a runaway nuclear reaction, resulting in a spectacular explosion that briefly outshines entire galaxies. What makes Type 1a supernovas so valuable is that they all have roughly the same intrinsic brightness. This means that astronomers can accurately estimate their distance based on their apparent brightness. If a Type 1a supernova appears faint, it must be very far away. If it appears bright, it must be relatively close. By studying these exploding stars, astronomers have been able to map the distances to galaxies billions of light-years away, far beyond what would be possible with other methods. But how can we be so sure that all Type 1a supernovas have the same intrinsic brightness? That's where the details get a little more complex. While they are not perfectly uniform, astronomers have developed ways to standardize them, accounting for slight variations in their light curves, the way their brightness changes over time. These corrections allow for incredibly precise distance measurements, making Type 1a supernovas essential tools for cosmology. It was, in fact, the study of Type 1a supernovas that led to one of the most profound discoveries in modern cosmology, the accelerating expansion of the universe. Another crucial cosmic yardstick is something known as redshift. Remember that light travels in waves, like ripples on a pond. As a light source moves away from us, the waves are stretched, increasing their wavelength. This is analogous to the Doppler effect, the change in pitch of a siren as it moves past you. The same principle applies to light, but instead of pitch, it's wavelength that changes. When the wavelength of light is stretched, it shifts towards the red end of the spectrum, hence the term redshift. The amount of redshift is directly proportional to the velocity at which an object is receding from us. The greater the redshift, the faster the object is moving away. This relationship, first observed by Edwin Hubble in the 1920s, is one of the cornerstones of modern cosmology. Hubble's law, as it's known, states that the farther away a galaxy is, the faster it is receding from us. This observation provided strong evidence for the expansion of the universe, the idea that space itself is stretching, carrying galaxies along with it. Redshift is an incredibly powerful tool for measuring distances to very distant objects far too faint to be seen with standard candles. By measuring the redshift of a galaxy, astronomers can estimate its distance, even if it's billions of light-years away. However, redshift measurements are not always straightforward. The redshift of a galaxy can be affected by factors other than the expansion of the universe, such as the galaxy's own peculiar motion through space. Astronomers must carefully account for these effects when using redshift to determine distances. So, how do these cosmic yardsticks help us gauge what lies beyond our sight, beyond the observable horizon? Indirectly. By mapping the distribution of galaxies and other structures within the observable universe, astronomers can develop models of the universe's overall structure and evolution. These models can then be used to extrapolate beyond the observable horizon to make predictions about what might lie beyond. For example, if we observe that the universe is remarkably uniform on the largest scales, with galaxies evenly distributed throughout space, we might infer that this uniformity continues beyond the observable horizon. This is known as the cosmological principle, the assumption that the universe is homogeneous and isotropic, meaning that it looks the same in all directions and at all locations. However, the cosmological principle is just an assumption, and it may not be true. It's possible that the universe beyond the observable horizon is fundamentally different from what we see within it. Perhaps it's filled with exotic structures, or perhaps it's governed by different laws of physics. The only way to truly know what lies beyond the horizon is to find ways to probe it directly, to develop new techniques that can circumvent the limitations imposed by the speed of light. Could gravitational waves, ripples in the fabric of space-time, offer a potential pathway? Or perhaps some yet undiscovered particle that interacts more weakly with matter, allowing it to travel from greater distances. These remain open questions, tantalizing possibilities that drive astronomers and physicists to continue pushing the boundaries of knowledge. The universe has whispered secrets, and we've learned to listen. How much more can we discern, and what new instruments will we need to build to hear the faintest, most distant echoes of the cosmos? Even with these ingenious methods, even with these cosmic mile markers stretching across billions of light years, we are still limited by what we can see. But what if the very fabric of space and time itself holds the key to understanding the universe's true extent, to unlocking the secrets that lie hidden beyond our observable horizon? What if the answer to whether the universe is finite or infinite is written into the very geometry of reality? Enter Albert Einstein, a name synonymous with genius, a mind that forever changed our understanding of gravity. Before Einstein, gravity was seen as a force, a pull between objects with mass. Newton's law of universal gravitation described this force with remarkable accuracy, but it didn't explain why gravity existed. Einstein, in his theory of general relativity, offered a revolutionary new perspective. He showed us that gravity isn't a force at all, but rather a consequence of the curvature of space-time. Imagine a trampoline, stretched taut and flat. This represents space-time, the four-dimensional fabric of the universe, woven together from 3 dimensions of space and 1 dimension of time. Now, place a bowling ball in the center of the trampoline. The ball creates a dip, a curvature in the fabric. If you roll a marble across the trampoline, it will be drawn towards the bowling ball, not because the bowling ball is pulling it, but because the marble is following the curve in the trampoline. This, in essence, is how gravity works, according to Einstein. Massive objects, like planets and stars, warp the fabric of space-time, causing other objects to move along curved paths. It's not that the Earth is pulling on the moon. It's that the Earth is creating a well in space-time, and the moon is simply following the contours of that well. But Einstein's theory goes far beyond just explaining gravity. It also has profound implications for the shape and fate of the entire universe. The geometry of space-time, its curvature and its overall structure, is determined by the amount of mass and energy it contains. And that geometry in turn dictates whether the universe is finite or infinite. Think of it this way. Imagine drawing a triangle on a flat piece of paper. The angles of that triangle will always add up to 180 degrees. But now, imagine drawing a triangle on the surface of a sphere, like the Earth. Because the surface is curved, the angles of the triangle will add up to more than 180 degrees. The geometry of the sphere dictates the properties of the shapes drawn on its surface. Similarly, the geometry of space-time dictates the properties of the universe. If the universe contains enough mass and energy, it will curve space-time in on itself, creating a closed, finite universe. In this scenario, if you were to travel far enough in one direction, you would eventually come back to your starting point, much like walking around the surface of the Earth. On the other hand, if the universe doesn't contain enough mass and energy, it will be negatively curved, creating an open, infinite universe. In this case, if you were to travel in a straight line, you would never come back to your starting point. The universe would stretch on forever, like an infinitely large saddle. Or, and this is where it gets really interesting, the universe could be flat. In a flat universe, the angles of a triangle would add up to exactly 180 degrees, just like on a flat piece of paper. A flat universe would also be infinite, stretching on forever in all directions. So, which of these possibilities is correct? Is our universe closed, open, or flat? The answer to that question depends on the amount of mass and energy it contains, and that's something that cosmologists are still trying to determine. But understanding the shape of space-time isn't just about determining whether the universe is finite or infinite. It's also about understanding its ultimate fate. Will the universe continue to expand forever, eventually becoming cold and dark? Or will gravity eventually win out, causing the universe to collapse in on itself in a fiery big crunch? The geometry of space-time holds the clues to the universe's ultimate destiny, and Einstein's theory provides us with the tools to decipher them. Is there a possibility of unexplored shapes? What if space-time is not as uniform and predictable as we believe? Are there regions where the fabric tears, folds, or creates unexpected connections? What mathematical frameworks do we need to develop to even describe these possibilities? If our reality is just one of potentially infinite others, does each follow the same universal laws? Or do some possess fundamental physical properties that we cannot even imagine? The shape of the cosmos and the ultimate destination of our journey are still up for debate. But what does all this mean for the ultimate question? Is the universe finite, or does it stretch on forever? Einstein's canvas gives us the framework, but to truly understand its contours, we need to zoom out, to look at the universe on the grandest scales imaginable. We need to determine its overall geometry, and that's where things get really interesting because current observations suggest something quite remarkable. Our universe appears to be incredibly, almost unbelievably, flat. Imagine a perfectly smooth tabletop extending in all directions without end. That's the kind of flatness we're talking about. But how can astronomers possibly measure the curvature of the entire universe? It's not like they can simply pull out a giant ruler and check if straight lines stay parallel over billions of light years. Instead, they rely on a variety of ingenious techniques, from mapping the distribution of galaxies to studying the subtle patterns in the cosmic microwave background. Think back to that afterglow of the Big Bang. Those tiny temperature fluctuations, those ripples in the early universe, aren't just random noise. They represent density variations, regions where matter was slightly more or slightly less concentrated. These density variations acted as seeds for the formation of galaxies and other large-scale structures. By studying the size and distribution of these fluctuations, astronomers can infer the geometry of the universe. It's like looking at the shadows cast by objects to determine the shape of the room. If the shadows are distorted in a particular way, you can conclude that the room is curved. Similarly, if the fluctuations in the CMB appear larger or smaller than expected, it would indicate that the universe is either closed or open. And what do the observations reveal? Again and again, the data points to a universe that is remarkably flat. From the Wilkinson Microwave Anisotropy Probe, or WMAP, to the Planck satellite, these powerful telescopes have meticulously mapped the CMB, providing increasingly precise measurements of its properties. And each time, the results confirm that the universe is flat, to within a margin of error of just 0.5%. That's an astonishing degree of flatness. Imagine building a table that's billions of light years across, and it's flat to within 0.5%. It's like trying to balance a pencil perfectly on its tip, an incredibly delicate balancing act. And it raises a profound question: why is the universe so flat? One possible explanation is cosmic inflation, that period of extremely rapid expansion in the first fraction of a second after the Big Bang. Inflation would have stretched out any initial curvature, smoothing out the universe and making it appear flat, much like blowing up a balloon makes its surface appear smoother. A flat geometry provides the simplest path to an infinite universe, stretching endlessly in all directions. If the universe is flat, then parallel lines will remain parallel forever, and space will extend without bound. It's the kind of universe that Isaac Newton envisioned, an infinite, unchanging void. But here's the rub. Is nearly flat enough to guarantee endlessness? That 0.5% margin of error leaves room for doubt. What if the universe is actually slightly curved, either closed or open, but on a scale so vast that we haven't been able to detect it yet? What if we're simply living in a tiny patch of a much larger curved universe? It's like trying to determine whether the Earth is flat by only looking at a small area. If you're standing in a field, the ground may appear perfectly flat. But if you travel far enough, you'll eventually notice the curvature of the Earth. Similarly, the universe may appear flat on the scales we can observe, but it could be curved on much larger scales, beyond our current ability to detect. This is where the debate rages on among cosmologists. Some argue that the universe is indeed perfectly flat, a consequence of inflation and the fundamental laws of physics. Others maintain that the evidence is still inconclusive, and that we need to continue searching for subtle signs of curvature. Perhaps future missions with even more powerful telescopes will finally settle the question. Perhaps we'll discover new ways to probe the geometry of the universe, to peer beyond the limitations imposed by the speed of light. Or perhaps the answer will remain forever elusive, a cosmic mystery that we can never fully unravel. But even if we can never definitively prove that the universe is infinite, the evidence for its flatness is compelling. It suggests that we live in a cosmos that is vast, expansive, and perhaps without end, a universe that is far larger and more awe-inspiring than we can possibly imagine. And that, in itself, is a truly remarkable discovery. Is the small possibility of an almost flat cosmos not enough to declare it is infinite? New data will be required, and perhaps a new way of thinking. But even the most meticulous measurements, the most sophisticated telescopes, leave us with a nagging doubt. Could there be something fundamentally wrong with our assumptions? Is there a missing piece of the puzzle that we haven't yet found? What if the universe played a trick on us, masking its true nature behind a veil of cosmic illusions? The near flatness we observe might be a local phenomenon, a cosmic accident masking a deeper, more complex reality. So, is there another explanation? An event so cataclysmic, so utterly transformative that it could account for the universe's incredible flatness and vastness? The answer, as improbable as it sounds, may lie in a period of unimaginable expansion, a cosmic growth spurt known as inflation. Imagine taking a deflated beach ball and, in the blink of an eye, inflating it to the size of our solar system, then continuing at speeds faster than light itself. This, in essence, is the theory of inflation, a mind-bending concept that proposes the universe underwent a period of exponential expansion in the first fraction of a second after the Big Bang. We are talking about a time so small that it is written as 0.00000000000000000000000000000000000000000000000000001 seconds. It solves some deep inconsistencies in Big Bang theory, but some scientists think the inflation hypothesis is its own biggest problem. It is mind-boggling, isn't it? But this seemingly outlandish idea actually solves several major cosmological puzzles. Remember the horizon problem, that nagging question of how the CMB could be so uniform across the entire sky, even in regions that were never in causal contact? Inflation provides a neat solution. By expanding the universe exponentially, it stretched out any initial irregularities, smoothing out the cosmos like wrinkles in a rapidly inflating balloon. This also explains the flatness that we see. Think of it in terms of our planet. From our perspective at ground level, the Earth looks flat even though the Earth is a sphere. Now image someone as small as an atom on an extremely large sphere. To the atom, the sphere looks flat. This is how we must understand our observable universe and how it relates to the rest of the universe. But inflation does more than just smooth out the universe. It also provides a mechanism for creating the seeds of galaxies and other large-scale structures. Quantum fluctuations, tiny ripples in the fabric of space-time, were stretched out by inflation, becoming the density variations that eventually collapsed under gravity to form the cosmic web we observe today. So, in a way, inflation is responsible for everything we see in the universe, from the smallest stars to the largest superclusters of galaxies. Now, a natural question arises: did this primordial growth spurt guarantee an infinite cosmos? The answer is not straightforward. Inflation, in itself, doesn't necessarily imply an infinite universe. It simply expands the universe dramatically, making it much larger than it would have been otherwise. However, many models of inflation do suggest that our observable universe is just a tiny speck within a vastly larger, possibly infinite reality. The thought is, if there was more to the balloon before inflation, there is certainly more balloon after inflation. Think of it like this. Imagine a loaf of raisin bread dough rising in an oven. Each raisin represents a galaxy, and the dough represents the expanding universe. Inflation is like giving the dough a massive initial push, causing it to expand far beyond its original size. Our observable universe would be just one raisin in this enormous loaf, completely unaware of the other raisins scattered throughout the dough. But what drove this incredible expansion? What force could have possibly powered such a cataclysmic event? This is one of the biggest mysteries in cosmology today, and the subject of intense research. The leading theory is that inflation was driven by a hypothetical field, known as the inflaton field, that permeated the early universe. This field possessed a unique property. It had a very high energy density, but exerted a negative pressure, causing space to expand exponentially. However, the exact nature of the inflaton field remains unknown. Was it a fundamental particle like the electron or the quark? Or was it something completely different, something that we haven't even conceived of yet? The answer to this question could revolutionize our understanding of particle physics and the fundamental laws of nature. The theory of inflation is not without its critics. Some scientists argue that it's too speculative, that it relies on too many unknown parameters. Others point to the fact that we have yet to directly detect any evidence for the inflaton field. But despite these challenges, inflation remains the leading explanation for the universe's early expansion, its flatness, and its large-scale structure. It is a theory that has been tested and refined over the years, and it continues to provide valuable insights into the origins and evolution of the cosmos. Perhaps as time passes, we will be able to fill in more of this picture. What will we see when we add data from the James Webb Space Telescope? Even with the tantalizing hints gleaned from inflation, a question lingers, as vast as the cosmos itself. What lies beyond the horizon? The simplest, perhaps most elegant answer is also the most unsettling: more of the same. Imagine a cosmic wallpaper, stretching infinitely in all directions, patterned with galaxies, stars, and planets, repeating ad infinitum. This idea, known as the cosmological principle, suggests that the universe on the largest scales is homogeneous and isotropic, meaning it looks the same everywhere and in every direction. Think of it as a cosmic ocean teeming with life, but so vast that we can only see a tiny corner of it. Are we destined to forever tread the shores of our observable universe, never knowing the true extent of the cosmic ocean beyond? The cosmological principle, while seemingly straightforward, has profound implications. It implies that the laws of physics are the same everywhere, that the processes that govern the formation of galaxies and stars here are the same as those billions of light years away. It also suggests that given enough space, anything that is possible is also probable. That means there could be countless other Earths, countless other solar systems, and perhaps even countless other civilizations, stretching endlessly beyond our view. Is this idea comforting or terrifying? The thought of an infinite universe teeming with possibilities is certainly awe-inspiring. But it also raises the specter of infinite repetition. If the universe is truly infinite, then there must be countless identical copies of ourselves living out the same lives on other planets, in other galaxies, forever. A cosmic Groundhog Day stretching into infinity. But what if the cosmological principle is wrong? What if the universe beyond the horizon is not the same as the universe we see? What if something fundamentally different awaits us? Something that challenges our understanding of physics, biology, and even consciousness itself. Perhaps the universe becomes increasingly strange and unrecognizable the further out you travel. Perhaps the familiar laws of physics break down, replaced by exotic forces and particles that we can't even imagine. Perhaps life, as we know it, is only possible in a small, localized region of the cosmos, surrounded by vast stretches of uninhabitable space. Think of it as venturing into an uncharted jungle. At first, you encounter familiar plants and animals, similar to those you've seen before. But as you delve deeper, you begin to encounter increasingly bizarre and unfamiliar creatures, plants that defy classification, and landscapes that seem to belong to another world. What if the universe is like that jungle, with our observable universe representing just the edge of a vast, unexplored wilderness? Is it possible that beyond our cosmic horizon lie realities so profoundly different that they defy human comprehension? Could there be entire regions of space where time flows backward, or where gravity repels instead of attracts? Could there be universes where the fundamental constants of nature are different, leading to entirely different kinds of matter and energy? The possibilities are endless, limited only by our imagination. Perhaps even more intriguing is the possibility that life itself could take on radically different forms beyond our horizon. We tend to assume that life must be based on carbon and water, like it is here on Earth. But what if there are other ways to build living organisms? What if there are creatures that breathe methane, or that are made of silicon instead of carbon? What if there are beings whose consciousness exists in a completely different dimension beyond our ability to perceive? Could it be that the very notion of what constitutes life is fundamentally different beyond our observable bubble? Perhaps there are entities so vastly different from ourselves that we wouldn't even recognize them as living beings. Imagine sentient clouds of plasma, or intelligent networks of dark matter, or beings whose very existence challenges our understanding of space and time. These are not just idle speculations. Scientists are actively searching for evidence that might contradict the cosmological principle, looking for subtle variations in the cosmic microwave background, or for anomalies in the distribution of galaxies. They're pushing the boundaries of our understanding, daring to ask questions that were once considered impossible. Is there some type of signal that could make its way to us? The truth is, we simply don't know what lies beyond the horizon. It could be more of the same, an endless repetition of cosmic structures, or it could be something completely different, something that will forever alter our understanding of the universe and our place within it. Whether it's an endless cosmic expansion or a landscape beyond imagination, the possibilities inspire us to keep searching, keep questioning, and keep pushing the boundaries of human knowledge. So how far are we willing to push? How much strangeness can we accept? The cosmos is waiting to see what, if anything, we will discover next. The question is not just whether the universe is infinite, but what happens if inflation, that mind-boggling expansion we discussed, never truly stopped everywhere? What if pockets of space are still inflating, spawning countless new universes like bubbles in a cosmic champagne? This is the staggering concept of the multiverse, a notion that shatters our comfortable picture of a single, self-contained reality. Our universe, the one we know and love, might just be one bubble in an infinite frothing sea of realities, each with its own unique laws of physics, its own history, its own destiny. Imagine an endless ocean, not of water, but of inflating space. Within this ocean, bubbles constantly form, expand, and perhaps even collide with each other. Each bubble represents a separate universe, a self-contained cosmos, with its own set of physical constants, its own particles, its own way of being. Some bubbles might be sterile and lifeless, governed by laws that preclude the formation of complex structures. Others might be teeming with life, perhaps even life far more advanced and bizarre than anything we can imagine. And still others may have started with a different set of physical laws altogether. But how could such a multiverse even arise? The answer, according to some theories, lies in the very nature of inflation. Once inflation starts, it may never truly stop completely. While it may end in some regions of space, giving rise to universes like our own, it could continue indefinitely in other regions, constantly spawning new bubble universes. This process is known as eternal inflation, and it leads to a multiverse that is not only vast, but also constantly growing and diversifying. Now, some might ask, where is the science? Is this just fanciful speculation, or is there any actual evidence to support the multiverse hypothesis? The truth is, evidence is difficult to come by. By definition, other universes are beyond our observable horizon, making direct observation impossible. However, there are some indirect ways to test the multiverse hypothesis. One possibility is to look for evidence of collisions between our universe and other bubble universes. If two bubbles were to collide, it could leave a detectable imprint on the cosmic microwave background, a subtle distortion in the afterglow of the Big Bang. Scientists are actively searching for these bruises on the CMB, hoping to catch a glimpse of another universe. It's like searching for ripples on a pond to infer the existence of a hidden island. Even if you can't see the island directly, its presence might be revealed by the waves it creates. Similarly, even if we can't see other universes, their existence might be revealed by their subtle effects on our own universe. But even if we do find evidence of collisions, it wouldn't necessarily prove the existence of the multiverse. There could be other explanations for the observed anomalies in the CMB. The multiverse remains a hypothesis, an intriguing but unproven idea. Another avenue of investigation involves exploring the fundamental constants of nature. These constants, such as the speed of light, the gravitational constant, and the charge of the electron, determine the properties of matter and energy. If these constants were even slightly different, the universe would be a very different place. Stars might not form, atoms might not bind together, and life as we know it would be impossible. The fact that the fundamental constants are so finely tuned for life has led some scientists to invoke the anthropic principle, which states that the universe must have properties that allow for the existence of observers, meaning us. But why is the universe so finely tuned? One possible explanation is that there are countless other universes with different values of the fundamental constants. We just happen to live in a universe where the constants are just right for life to exist. Think of it as a cosmic lottery. There are countless tickets, each with a different combination of numbers. We just happen to have won the jackpot, living in a universe that is perfectly suited for life. But what are the odds of winning such a lottery? If there are an infinite number of universes, then even the most improbable outcomes become inevitable. So, could beyond the horizon actually mean crossing into entirely different universes? Could we one day, perhaps through some unimaginable technological breakthrough, find a way to travel to another bubble in the multiverse? The idea is certainly tantalizing, but it also raises profound questions. What would we find in another universe? Would the laws of physics be the same? Would life exist? Would we even be able to survive? Perhaps the most fundamental question of all is this: is our reality unique, or is it just one of many? Are we special, or are we just another bubble in an infinite sea? The answer to this question could have profound implications for our understanding of ourselves, our place in the universe, and the very nature of reality. The possibility of a multiverse challenges us to reconsider everything we thought we knew. Could it be that the reality we experience is just a tiny sliver of a much larger, more complex, and ultimately unknowable cosmos? And if that is the case, what other mind-bending possibilities still await discovery? But what if our intuition, shaped by our experience on a seemingly flat Earth, is leading us astray? What if the infinite multiverse, with its countless bubble universes, isn't the only game in town? What if the universe is, in fact, finite, but in a way that defies our everyday understanding of boundaries and edges? Imagine a cosmos not like an ever-expanding ocean, but like the surface of a giant, unimaginably large balloon. A balloon so immense that, from our vantage point, it appears flat, but is, in reality, curved back on itself. This is the concept of a closed, spherical universe, a universe that is finite in size, containing a limited amount of space, but without any edge or boundary. It's a counterintuitive idea, one that challenges our deepest assumptions about the nature of reality. How can something be finite yet have no end? How can we reconcile this seemingly paradoxical notion with our everyday experience? Think of an ant crawling on the surface of a basketball. To the ant, the surface appears flat, and it can walk in any direction without ever reaching an edge. Yet, the surface is finite, and if the ant were to walk far enough in one direction, it would eventually come back to its starting point. Now, extrapolate that idea to 3 dimensions. Imagine that instead of living on the surface of a sphere, we live within the 3-dimensional equivalent of a sphere, a space that is curved back on itself in all directions. In such a universe, there would be no edge, no boundary, but the total volume of space would be finite. It's like a cosmic hall of mirrors, where if you looked far enough in one direction, you'd eventually see the back of your own head. But what would such a universe look like? Would we be able to see multiple images of the same galaxies, ghostly echoes of the past repeating across the sky? Would the familiar laws of physics still hold true, or would they be subtly distorted by the curvature of space? One of the most intriguing consequences of a closed, spherical universe is the possibility of cosmic travel on an epic scale. Imagine setting out on a journey to explore the cosmos, traveling in a straight line through the vast expanse of space. In an infinite universe, you would travel forever, never reaching a destination. But in a closed universe, your journey would eventually bring you back home, to the very point where you started. It's a cosmic loop, a journey without end, but with a guaranteed return. Like Magellan circumnavigating the Earth, but on a scale that encompasses the entire universe, what discoveries would you make on such a journey? What strange and wondrous sights would you behold? And what would it feel like to finally arrive back home knowing that you had traveled the farthest distance possible, yet ended up exactly where you began? However, detecting the curvature of a closed universe is no easy task. The curvature might be so subtle, so gradual, that it's undetectable on the scales we can currently observe. It's like trying to determine the curvature of the Earth by only looking at a small patch of land. The ground may appear flat, but if you zoom out far enough, you'll eventually see the curvature. To detect the curvature of a closed universe, we would need to observe extremely distant objects whose light has traveled for billions of years across the vast expanse of space. We would need to look for subtle distortions in the images of these objects, distortions caused by the curvature of space bending the path of light. Think of it as looking through a curved lens. The lens distorts the images of objects, making them appear larger or smaller, stretched or compressed. Similarly, the curvature of a closed universe would distort the images of distant galaxies, providing clues about the overall geometry of space. But even if we could detect the curvature of space, it wouldn't necessarily prove that the universe is closed. There are other possibilities, other geometries that could produce similar effects. The universe could be open, shaped like an infinite saddle, or it could be even more exotic, with a topology that defies our everyday understanding. Perhaps the universe is not simply curved, but also twisted, folded, or even knotted in some unimaginable way. Perhaps space is not continuous, but discrete, made up of tiny, indivisible units like pixels on a screen. Perhaps there are hidden dimensions curled up at every point in space, dimensions that we cannot directly perceive, but that influence the geometry of the universe. What instruments would we need to explore this type of space? Could these new technologies show us what we need to see? The possibilities are endless, and the quest to understand the shape of the universe is one of the greatest intellectual adventures of our time. It's a journey that takes us from the smallest scales of quantum mechanics to the largest scales of cosmology, from the familiar world of everyday experience to the strange and wondrous realms of the unknown. And, as we continue on this journey, we may find that the universe is even more bizarre, more beautiful, and more mysterious than we ever imagined. But what if the grand cosmic design isn't a perfectly curved sphere gently looping back on itself? What if instead the universe is shaped more like a colossal saddle, stretching out infinitely in all directions, a mind-bending landscape of negative curvature? This is the possibility of an open universe, a cosmos without end, but one with geometric properties so strange they defy our everyday intuition. Forget those nice Euclidean rules you learned in school, because in this universe parallel lines don't stay parallel, they diverge, drifting further and further apart like ships lost at sea. And triangles? Well, their angles add up to less than 180 degrees. It's a geometry that would have made Euclid himself scratch his head, a reality where the familiar rules of space simply don't apply. Imagine riding a horse across an infinite saddle. No matter how far you travel, you'll never reach an edge. You'll never loop back to where you started. The landscape simply stretches on, endlessly. That's the essence of an open universe, a cosmos that is not only infinite in extent, but also negatively curved. This curvature, this saddle shape, has profound implications for how light travels, how galaxies form, and even how we perceive the universe itself. Think about those laser pointers we used to play with as kids. On a flat surface, the beam travels in a straight line, never diverging or converging. But on a curved surface, the beam behaves differently. On a sphere, the beams will slowly converge, eventually meeting at a single point. That's how a magnifying glass works, focusing the sun's rays to start a fire. But on a saddle-shaped surface, the laser beams will diverge, spreading out and becoming weaker as they travel. The same principle applies to light traveling through the universe. In a closed, spherical universe, light rays would eventually converge, creating distorted images of distant objects. But in an open, saddle-shaped universe, light rays would diverge, making distant objects appear smaller and fainter than they actually are. It's as if the universe itself is a giant diverging lens, spreading out the light and making it harder to see what lies far away. But the implications of a hyperbolic reality go beyond just the way light travels. They also affect the way matter clumps together to form galaxies and other structures. In a flat universe, gravity has to work a little bit harder to pull matter together, since space is expanding at a constant rate. But in an open, negatively curved universe, gravity has an even harder time, since the expansion is even faster. It's like trying to build a sandcastle on a beach with a strong current. The current keeps washing away the sand, making it difficult to create a stable structure. Similarly, the rapid expansion of an open universe makes it harder for gravity to overcome the expansion and pull matter together. This means that galaxies in an open universe would tend to be smaller and less dense than galaxies in a flat or closed universe. What would it be like to actually live in such a hyperbolic reality? Would we even be able to tell the difference? At first glance, the answer might seem to be no. On small scales, the universe would look pretty much the same, whether it's flat, closed, or open. But as we look out further and further into space, the subtle effects of the curvature would become more apparent. Distant galaxies would appear fainter and smaller. The distribution of galaxies would be slightly different. The cosmic microwave background would have a slightly different pattern of temperature fluctuations. It would be like living in a funhouse mirror where everything looks just a little bit distorted. You might not notice it at first, but after a while you'd start to realize that something is not quite right. What about our own solar system, our own planet? Would the laws of physics still apply in the same way? Would life still be possible? The answer, as far as we know, is yes. The laws of physics are thought to be universal, applying everywhere in the universe, regardless of its curvature. And life, as far as we can tell, is remarkably adaptable, capable of thriving in a wide range of environments. However, there might be some subtle differences. The curvature of space could affect the orbits of planets, the behavior of light, and even the flow of time. It's like living in a slightly different version of reality, where the familiar rules are tweaked just a little bit. Would these changes be noticeable on a personal level? Perhaps not, but on a cosmic scale they would be profound. So, as we continue to probe the depths of the cosmos, mapping the distribution of galaxies and analyzing the faint glow of the early universe, will we uncover evidence of this infinite saddle? Or will the universe continue to surprise us, revealing new and even more bizarre geometries beyond our wildest imaginations? Even as we grapple with these mind-bending possibilities, a fundamental question remains. How can something be finite, yet have no boundary? It sounds like a riddle straight out of a science fiction novel, a paradox that defies logic and intuition. But believe it or not, mathematicians and cosmologists have been wrestling with this very question for decades, and the answers they've come up with are truly extraordinary. Prepare to have your perception of reality stretched to its absolute limit. Think about the classic arcade game Pac-Man. The screen is finite, it has a definite width and height. Yet when Pac-Man reaches the edge of the screen, he doesn't bump into a wall or fall off the edge. Instead, he reappears on the opposite side, continuing his endless pursuit of power pellets and fleeing from those pesky ghosts. The Pac-Man screen is a two-dimensional example of a space that is finite but unbounded, a world without edges. Now, imagine that we live not in 2 dimensions but in 3. Could our universe be similar to the Pac-Man screen, wrapping around on itself in some way, so that if we traveled far enough in one direction, we would eventually reappear on the other side? It's a mind-boggling idea, but it's not as far-fetched as it might seem. Another helpful analogy is the surface of a donut, also known as a torus. An ant crawling on the surface of a donut can travel endlessly without ever reaching an edge. It can go around the hole or around the outside and just keep going forever. The surface of the donut is finite in area, but it has no boundary. These two-dimensional examples help us to visualize how a three-dimensional space can be finite but unbounded. But how can we tell if our universe is actually shaped like this? How can we test this bizarre hypothesis? The answer lies in looking for repeating patterns in the cosmos, for ghostly echoes of distant objects that have traveled all the way around the universe and back to us. Imagine that we are looking at a distant galaxy, billions of light years away. In a normal, infinite universe, we would only see one image of that galaxy. But in a closed, unbounded universe, there might be multiple images of the same galaxy, appearing in different parts of the sky. These images would be like cosmic déjà vu, providing clues about the size and shape of the universe. It's like looking into a room full of mirrors. You see multiple reflections of the same objects, each one showing a different perspective. Similarly, in a closed universe, we might see multiple reflections of the same galaxies, each one showing us a different view of the cosmos. But finding these repeating patterns is an incredibly difficult task. The universe is vast, and the distortions caused by the curvature of space could make the images difficult to recognize. Scientists are currently scouring the cosmic microwave background, that faint afterglow of the Big Bang, for evidence of these repeating patterns. They're looking for circles in the sky, regions where the temperature fluctuations are correlated in a particular way. These circles could be the telltale signs of a closed, unbounded universe. However, even if we do find these circles, it wouldn't necessarily prove that the universe is shaped like a simple sphere or a torus. There are other, more complex topologies that could produce similar patterns. Perhaps the universe is not just curved, but also twisted, folded, or even knotted in some unimaginable way. Think about a Mobius strip, a strip of paper that has been twisted and joined at the ends to form a loop. A Mobius strip has only one side and one edge. If you draw a line down the center of the strip, you'll eventually come back to your starting point without ever crossing an edge. Could our universe be something like a three-dimensional Mobius strip, a space that is both finite and endlessly twisted? These concepts challenge the very core of our understanding of space and time. We've always assumed that space is something that extends infinitely in all directions, but what if that assumption is wrong? What if space is actually a finite, self-contained entity, a cosmic bubble that is both limited in size and yet without boundary? It's a mind-bending thought, one that forces us to question everything we thought we knew about the nature of reality. But if it's true, it would revolutionize our understanding of the universe and our place within it. Would this change the way we explore the great beyond? Even as we paint these grand portraits of the cosmos, wielding supernovas as our brushes and redshift as our palette, a persistent question tugs at the edge of our minds. Are we missing something? Is there a hidden architecture, a cosmic blueprint that our current maps fail to capture? What if the universe in its infinite vastness is also playing a game of cosmic hide-and-seek, concealing its true nature behind a veil of repeating patterns? Think of it like this. Imagine staring at a seemingly random collection of stars, only to realize that, with a little imagination, they form a recognizable constellation. Could the universe itself be a giant constellation, a pattern waiting to be deciphered? If the universe is indeed finite, curling back on itself like some unimaginable origami creation, then light from distant objects would eventually loop around, offering us multiple views of the same celestial bodies. It would be like standing in a hall of mirrors, surrounded by endless reflections. But instead of mirrors, it's the very fabric of space that is reflecting these images, bending the light and creating ghostly echoes of galaxies long past. These echoes would appear as repeating patterns in the sky, subtle correlations in the distribution of galaxies and the cosmic microwave background. The challenge, of course, is to find these patterns, to distinguish them from the random noise of the cosmos. It's like searching for a specific grain of sand on a beach that stretches to infinity. Scientists are employing ingenious techniques to sift through the data, using sophisticated algorithms to identify subtle correlations and repeating structures. They're scouring the cosmic microwave background, searching for circles in the sky, regions where the temperature fluctuations are correlated in a particular way. These circles, if they exist, could be the fingerprints of a finite universe, evidence that space is indeed wrapping around on itself. But why circles? Imagine shining a flashlight in a closed room. The light will bounce off the walls, creating multiple images of the flashlight itself. If the room is perfectly spherical, the images will form circles around the room. Similarly, if the universe is closed and spherical, the light from distant objects will loop around, creating circular patterns in the sky. Of course, the universe is far more complex than a simple sphere. It might be twisted, folded, or even knotted in ways that we can't even imagine. This means that the repeating patterns might not be perfect circles, but distorted and warped in complex ways. It's like trying to recognize a familiar face in a funhouse mirror. The features are still there, but they're stretched and distorted, making them difficult to identify. So, how close are we to finding these cosmic echoes? Are we on the verge of unraveling the universe's deepest secrets? Or are we chasing a mirage, a cosmic illusion that will forever elude our grasp? The truth is, the search is still in its early stages. Scientists are constantly developing new and more powerful techniques for analyzing the data, pushing the boundaries of what is possible. Imagine the excitement, the sheer exhilaration of being the one to discover the first undeniable evidence of a finite universe. It would be a discovery that would rewrite the textbooks, a moment that would forever change our understanding of our place in the cosmos. What if this discovery is just around the corner? And if it is, how will it change the way that we see the universe? How will it change the way that we see ourselves? And so, we embark on this quest to find those cosmic echoes, to discern order from chaos, whispering a silent question to ourselves. Are we destined to forever remain within our cosmic snow globe, forever prevented from truly grasping the universe's ultimate form? Are we simply trapped by physics? Is this cosmic limit unbreakable? Even with our most advanced telescopes, are we forever confined to seeing only a fraction of what's out there? We equip them with the most advanced components and the most precise sensors, yet we find that those distant galaxies become forever more faint. Their signals weaken as they stretch across the unfathomable distances, and the curvature of space acts as a sort of veil. How can something that has no mass stop us from looking beyond this boundary? Consider the light from our own sun. It takes approximately 8 minutes for that light to travel the 149,600,000 kilometers to Earth. This relatively short delay has no real impact on our lives. Yet imagine a cosmic event unfolding 13 billion years away. By the time its light finally reaches our telescopes, the source itself has likely changed dramatically, or may no longer even exist. We look into the past, yet the past is not today. That unbreakable limit, the speed of light, is a cornerstone of our current understanding of physics. Einstein's theory of special relativity dictates that nothing can travel faster than light in a vacuum. So the limitation is fundamental. But it isn't simply a technological problem. We can't just build a bigger, better telescope and magically see further. The speed of light is an absolute barrier, a cosmic speed limit enforced by the very laws of nature. The implication is simple. There are portions of the universe whose light will never reach us. Ever. But does this mean the question of infinity is forever beyond experimental reach? Are we doomed to forever ponder the cosmos with incomplete information? The answer, thankfully, is not necessarily. While we may never directly see what lies beyond the observable horizon, there are indirect ways to gain insight, to infer the properties of the universe beyond our immediate view. Think about the way sound waves can travel around corners. Even if you can't see the source of the sound, you can still hear it and learn something about its location and intensity. Similarly, even though we can't see beyond the observable horizon, there may be other signals, other forms of radiation or exotic particles that can reach us from those distant realms. One possibility lies in the study of the cosmic microwave background. Remember this afterglow from the Big Bang? It's the oldest light in the universe. But even though we can only see it from a certain distance, the CMB contains information about the early universe, about the conditions that existed before galaxies and stars even formed. And this data can be used to test cosmological models, to probe the geometry of spacetime, and to infer the properties of the universe on the largest scales. If the universe is closed, like a sphere, we might see some distortions and patterns on the CMB that would be radically different from what we would see if the universe is open like a saddle. Gravitational waves offer another avenue to circumvent the unbreakable limit. Unlike light, gravitational waves are ripples in the fabric of space-time itself, caused by accelerating masses. These waves travel at the speed of light, but they interact very weakly with matter. So they travel through vast stretches of the cosmos practically unimpeded. Can they show us more? Imagine two black holes colliding billions of light years away. The collision would generate a burst of gravitational waves that would ripple outwards, carrying information about the masses, spins, and orbits of the black holes. By detecting these gravitational waves, we could learn about events that are completely invisible to our telescopes, events that occurred long before light had a chance to reach us. What is beyond the horizon? Black holes or white holes? So, although the speed of light poses a fundamental limitation on our ability to directly observe the universe, it doesn't necessarily mean that the question of infinity is forever beyond our experimental reach. There are indirect ways to probe the cosmos, to glean clues from the faint echoes of the Big Bang, the subtle ripples in space-time, and perhaps even from entirely new phenomena that we have yet to discover. The quest for knowledge is unrelenting, and the universe, however vast and mysterious, may yet yield its secrets, offering a glimpse beyond the unbreakable limit. Even as we stand humbled by the potential for unbreakable limits, a far more unsettling and perhaps liberating question emerges from the depths of an infinite cosmos. What if the universe in its relentless expansion isn't just indifferent to our existence, but actively, mathematically, demands our repetition? What if an infinite universe, governed by the laws we observe, leads to the inescapable conclusion that there are infinite copies of you, living out infinite versions of your life, scattered across the cosmos? It's a concept that can induce a peculiar mix of existential dread and dizzying wonder. One must ask, what is infinite? Is it simply a really, really big number? Or is it something that transcends our ability to comprehend, a concept so vast it shatters the very foundations of our understanding of reality? Imagine standing before a cosmic mirror, stretching out to infinity in all directions. In that mirror, you see not one reflection, but an infinite cascade of reflections, each slightly different, each representing a different possibility. In some reflections, you're a celebrated scientist, unraveling the mysteries of the universe. In others, you're a struggling artist, pouring your soul into canvases that may never be seen. And in still others, you might not even exist at all, replaced by someone else, someone who took a different path, made a different choice. But are you still you? This thought experiment isn't just philosophical ramblings. It stems from a collision of cosmology, mathematics, and a dash of unsettling logic. If the universe is truly infinite and relatively uniform, meaning the density of matter and energy is roughly the same everywhere, then the number of possible particle arrangements within a given volume of space is finite. It's an incredibly large number, to be sure, but still finite. And as has been mentioned, if you have infinite space, even the most improbable events must occur and then recur an infinite number of times. Think of it like shuffling a deck of cards. With 52 cards, there are only a limited number of possible arrangements. If you shuffle the deck enough times, you're bound to repeat a previous arrangement, even if it takes trillions upon trillions of shuffles. Now, imagine shuffling a deck of cosmic proportions, a deck consisting of all the particles in the universe. The number of possible arrangements is astronomical, but still finite. And in an infinite universe, those arrangements must repeat not just once, but infinitely many times. This means that somewhere out there, perhaps many billions of light years away, there exists a planet identical to Earth with a solar system identical to ours and a person identical to you, living out a life that is indistinguishable from yours, at least until some point. Because even the slightest quantum fluctuation, the tiniest butterfly effect, can cause those parallel lives to diverge, leading to vastly different outcomes. Maybe this, you will win the lottery. But what does it even mean to say there is another you out there? Are these copies truly you, or are they merely identical automatons, lacking the unique spark of consciousness that defines us? This is where the philosophical implications become truly mind-bending. If consciousness is simply the result of complex interactions between neurons in the brain, then any system with the same configuration of neurons would presumably have the same consciousness. That means that those identical copies of you would not just look and act like you, they would be you, experiencing the same thoughts, feelings, and sensations. It's a dizzying thought, isn't it? That somewhere out there, you are experiencing this very moment again, perhaps making a different decision, perhaps reacting in a slightly different way. What if that copy, the you on that distant planet, decided to quit their job and travel the world? Would that decision have any impact on your life here on Earth? Would you suddenly feel an inexplicable urge to pack your bags and leave everything behind? Or would you simply continue on your current path, blissfully unaware of the other you living out a different version of your life? And the paradox deepens. If there are infinite copies of you, then there are also infinite copies of everything else. Infinite copies of your loved ones, your friends, your enemies. Infinite copies of historical events, scientific discoveries, artistic masterpieces. An infinite library of everything that has ever been, is now, or could ever be. Can reality truly handle such vastness? What if the universe is not quite as uniform as we think it is? What if there are regions where the laws of physics are slightly different, or where the density of matter is significantly higher or lower? Would this change the equation? Would it mean that the copies of ourselves are not truly identical but only approximate? Perhaps this is why we, as a species, find the concept of infinity so difficult to grasp. Our brains, evolved to navigate the finite world of our ancestors, are simply not equipped to comprehend the sheer scale and complexity of the cosmos. We cling to the notion of uniqueness, of individuality, because it gives us a sense of meaning and purpose. But what if that notion is just an illusion, a comforting fiction that we tell ourselves to make sense of an infinite, indifferent universe? If these concepts are hard to grasp for you, perhaps you would like to grab a nice beverage before continuing to contemplate these cosmic possibilities. But even confronting the unsettling implications of infinite doppelgangers, the nagging question of origin persists. The Standard Model, the Big Bang with its inflationary epoch, explains so much, but what if it isn't the only story? What if there are entirely different cosmic scripts, alternative beginnings that reshape our understanding of the universe's extent and its ultimate nature? Can alternative cosmologies sidestep the very question of infinity altogether? Buckle up, because we're about to venture beyond the well-trodden path into the realm of speculative physics, where the origins of everything are up for grabs. The Big Bang model, with its explosive start and subsequent inflation, is incredibly successful. It explains the cosmic microwave background, the abundance of light elements, and the large-scale structure of the universe with remarkable accuracy. But the Standard Model is not without its challenges. What caused the Big Bang? What existed before the inflationary epoch? And what is the true nature of dark energy, the mysterious force driving the accelerating expansion of the universe? These are questions that continue to baffle cosmologists, prompting them to explore alternative scenarios, ones that challenge the very foundations of the Big Bang paradigm. Consider, for example, the concept of cyclic universes. Imagine a cosmos that doesn't begin with a singular event, but instead undergoes endless cycles of expansion and contraction, birth and rebirth. In this model, our universe is not the first, nor will it be the last. It's just one in an infinite series of universes, each emerging from the ashes of the previous one. Think of it as a cosmic phoenix, constantly rising from its own ashes, forever renewing itself in an endless cycle of creation and destruction. One popular version of the cyclic universe involves a big bounce replacing the Big Bang. Instead of a singularity, an infinitely dense point from which everything expands, the universe collapses to a minimum size before bouncing back into a new phase of expansion. What triggers this bounce? Some theories propose exotic forms of matter or energy that violate the usual laws of physics, while others suggest that quantum effects near the minimum size prevent the universe from collapsing all the way to a singularity. Now, does a cyclic model sidestep the question of infinity? In some ways, yes. If the universe has always existed, cycling through endless phases of expansion and contraction, then there is no need for a beginning, no need for a singular event that created everything out of nothing. The universe is simply eternal, forever changing, forever evolving, but never truly beginning or ending. But cyclic models aren't the only alternative to the Big Bang. There are other, even more radical scenarios that challenge our understanding of the universe's origins. Think of the ekpyrotic universe. It proposes that our universe was created from the collision of two brains, higher dimensional objects floating in a larger space. It is hard to imagine, but think of two sheets of paper floating together and creating a spark upon impact that creates a new universe. This collision would have released an enormous amount of energy, triggering the expansion of our universe and seeding it with the density fluctuations that eventually formed galaxies and stars. The ekpyrotic model, like the cyclic universe, attempts to avoid the singularity of the Big Bang, but it does so by invoking extra dimensions, hidden realms beyond our everyday perception. What are these brains, and where did they come from? These are questions that push the boundaries of our understanding, forcing us to confront the possibility that our universe is just a small part of a much larger, more complex reality. Another alternative is the steady-state theory. This theory rejects the idea of an expanding universe altogether. Instead, it proposes that the universe has always been the same, with new matter continuously being created to fill the void left by the expansion. The theory was proposed by Fred Hoyle, among others, and it gained some popularity. It does have some challenges that it could not overcome, such as the explanation of the cosmic microwave background. Hoyle also had some pushback for not recognizing the importance of the Big Bang theory. These models are just a few examples of the alternative cosmologies that scientists are exploring. They may seem outlandish, even fantastical, but they represent a vital part of the scientific process. By challenging the standard model, by pushing the boundaries of what is possible, we can gain a deeper understanding of the universe and our place within it. What if the key to understanding the universe's origin lies not in finding a single definitive answer, but in embracing the multiplicity of possibilities? Perhaps the universe is not governed by a single set of laws, but by a multitude of different rules, each operating in different regions of space or at different times in cosmic history. Perhaps the universe is not a single coherent entity, but a patchwork of different realities, constantly interacting and influencing one another. Perhaps the journey to understand the universe's origins is a journey without end, a quest that will forever challenge our assumptions, expand our horizons, and inspire us to keep asking the most fundamental questions of all. The theories may be outlandish, but they do show that we are always exploring and questioning. Where will these questions take us? And so we find ourselves standing at a crossroads, not just in space, but in time. The questions we've explored, the theories we've considered, all lead to a single, unavoidable point. What is the ultimate destiny of the universe? Is its fate intertwined with its size, its shape, its very nature? Will it expand forever, leading to a cold, dark, and lonely existence? Or will gravity, that relentless cosmic force, eventually win, pulling everything back together in a cataclysmic embrace? Consider a pebble thrown into a pond. The ripples spread outwards, their energy dissipating over time until they eventually fade into nothingness. Is this the fate of our universe? A slow, inevitable decline into a state of utter stillness? The current data suggests that the expansion of the universe is not only continuing, but actually accelerating, driven by that mysterious force we call dark energy. If this acceleration continues unchecked, the universe will become increasingly dilute, with galaxies drifting further and further apart until they are no longer visible to one another. Stars will eventually burn out, black holes will evaporate, and the universe will descend into a state of maximum entropy, a cold, dark, and desolate expanse where nothing new can ever happen. This is the scenario known as the Big Freeze, also sometimes referred to as heat death. It sounds rather bleak, doesn't it? A cosmic wasteland stretching out to infinity, devoid of light, life, and hope. But before you succumb to existential despair, consider the alternative. What if dark energy is not constant? What if its strength diminishes over time, allowing gravity to regain its dominance? What if instead of expanding forever, the universe eventually begins to contract, pulling everything back together in a process that is the reverse of the Big Bang? Imagine a film running backwards, galaxies rushing towards each other, the cosmic microwave background heating up, and the universe becoming increasingly dense and hot. Eventually, everything would be compressed into a single point, a singularity of infinite density and temperature, a mirror image of the Big Bang. This is the Big Crunch, the ultimate cosmic recycling event. This scenario has a certain poetic appeal, doesn't it? A universe that is born from a singularity, expands and evolves for billions of years, and then collapses back into another singularity, ready to begin the cycle anew. It's a cosmic Ouroboros, a snake eating its own tail, a symbol of eternal renewal. But which of these scenarios is more likely? The answer, as always, depends on the amount of dark energy in the universe, the shape of space-time, and the interplay between gravity and expansion. If the universe is closed, like a sphere, then the big crunch is the more likely outcome. The curvature of space-time would eventually cause the expansion to slow down and reverse, leading to a catastrophic collapse. On the other hand, if the universe is flat or open like a saddle, then the big freeze is the more likely fate. The expansion would continue forever, driven by dark energy, until the universe becomes a cold, dark, and empty void. However, there are other possibilities, more exotic scenarios that could alter the universe's destiny in unexpected ways. Consider the Big Rip. In this scenario, dark energy becomes increasingly powerful over time, eventually overcoming all other forces in the universe. Galaxies would be torn apart, stars would be ripped from their galaxies, planets would be ripped from their stars, and eventually, even atoms would be ripped apart, leaving nothing but a sea of elementary particles flying apart at ever-increasing speeds. It's a rather violent and dramatic end, isn't it? A cosmic apocalypse of unimaginable proportions. Then again, should not forget about the big change. This possibility suggests that our universe is metastable, and it could decay into a different state. So does the concept of infinity change depending on the universe's ultimate destiny? Absolutely. In a big freeze scenario, the universe becomes increasingly dilute, with matter and energy spreading out to infinity. The density of matter would approach zero, and the universe would become increasingly empty and uniform. In a big crunch scenario, on the other hand, the universe would become increasingly dense, with matter and energy concentrated into a single point. The density of matter would approach infinity, and the universe would become increasingly chaotic and unpredictable. But what if the universe's fate is not determined by a single cataclysmic event, but by a series of smaller, more localized changes? What if the universe is not destined to end in a bang or a whimper, but in a slow, gradual transformation, a cosmic metamorphosis that unfolds over unimaginable timescales? What secrets still lie hidden in the fabric of space-time, waiting to be revealed? The story of the universe is far from over, and there are undoubtedly many more twists and turns to come. The ultimate chapter remains unwritten, and it is up to us, with our insatiable curiosity and our relentless pursuit of knowledge, to continue exploring the cosmos, to continue asking the big questions, and to continue pushing the boundaries of human understanding. Even as we stand humbled by the potential for unbreakable limits, even as we find repeating structures and patterns, we still wonder, what are we missing? But hold on, what if the very fabric of our reality is being stretched and pulled in ways we can barely comprehend? What if the universe isn't just expanding, but accelerating its expansion, like a cosmic roller coaster gaining speed on a downward plunge? A mysterious force is at play, an enigma that throws a wrench into our understanding of gravity, distance, and the shape of things to come. It's a puzzle that has scientists scratching their heads, a cosmic whodunit with implications that could rewrite the story of the universe. This brings us to dark energy. It's an appropriate name, isn't it? Dark, mysterious, unknown. Unlike ordinary matter and energy, which tend to clump together under the influence of gravity, dark energy seems to be pushing things apart, driving the accelerating expansion of the universe. Imagine, if you will, an invisible hand, gently but firmly pushing galaxies away from each other, stretching the fabric of space-time itself. That, in essence, is the effect of dark energy. But what exactly is dark energy? That's the million-trillion-dollar question, the holy grail of modern cosmology. The truth is, we really don't know. It's one of the biggest mysteries in science today, a problem that has stumped some of the greatest minds of our time. One leading theory proposes that dark energy is a property of space itself, an inherent energy density that permeates the vacuum. This idea, known as the cosmological constant, was actually proposed by Albert Einstein himself, although he later retracted it, calling it his greatest blunder. Ironically, it may turn out that Einstein was right all along. Another possibility is that dark energy is a new type of dynamic energy field, something that changes over time and space. This idea, known as quintessence, suggests that dark energy is not constant but rather a fluid-like substance that can evolve and interact with other components of the universe. Think of it like a cosmic seesaw, with dark energy on one side and gravity on the other. For most of the universe's history, gravity was the dominant force, pulling matter together to form galaxies and stars. But as the universe expanded and became more dilute, the influence of gravity weakened, while the influence of dark energy remained constant. Eventually, dark energy took over, tipping the seesaw and causing the expansion to accelerate. But how does this accelerating expansion impact our ability to probe the cosmos's edge? The answer, unfortunately, is not encouraging. As distant galaxies are pushed away from us faster and faster, their light becomes increasingly stretched, a phenomenon known as cosmological redshift. This redshift makes it harder and harder to see these galaxies as their light is shifted to longer and longer wavelengths, eventually fading into the infrared and radio spectrum. It's like trying to listen to a faint whisper from across a vast canyon. The further away the speaker is, the harder it is to hear their voice, as the sound waves are scattered and distorted by the wind and the terrain. Similarly, the further away a galaxy is, the harder it is to see its light, as the photons are stretched and scattered by the expanding universe. This means that our effective observable universe is actually shrinking over time. Galaxies that were once visible to us are now receding beyond our horizon, their light forever lost to our telescopes. It's a chilling thought, that we are slowly but surely losing our connection to the wider cosmos. Does dark energy guarantee a lonely future, even in an infinite universe? The answer, sadly, seems to be yes. If the accelerating expansion continues unchecked, the universe will become increasingly desolate, with galaxies drifting further and further apart until they are completely isolated from one another. Imagine a future where our Milky Way galaxy is the only island in a vast empty ocean of space. There would be no other galaxies visible in the night sky, no other civilizations to communicate with, no other worlds to explore. Just us, alone in the darkness, forever cut off from the rest of the cosmos. A truly lonely future indeed. Is it possible to imagine any way to counteract this destiny? Could there be some future technology, some unforeseen breakthrough that would allow us to overcome the limitations imposed by dark energy? It would take some sort of force to overcome the expansion, but what? As we continue to explore the mysteries of the cosmos, let's see where it takes us. Even as we contemplate the lonely fate that dark energy might have in store, we must ask ourselves, is there a realm that lies not just beyond our distance, but beyond our very senses? Could the answer to the universe's greatest mysteries lie not in bigger telescopes or more powerful detectors, but in understanding dimensions that are so infinitesimally small that they exist beyond our common perception? Modern physics is hinting at realities that go far beyond our familiar three spatial dimensions. We experience length, width, and height every single day. They're the pillars of our physical intuition. But what if these aren't the only dimensions? What if there are others curled up so tightly that they are invisible to us, yet are shaping the very fabric of reality? These whispers of other dimensions come from one of the most ambitious and controversial theories in modern physics, string theory. Imagine a garden hose. From a distance, it looks like a one-dimensional line, but if you get closer, you'll see that it actually has a second dimension, the circumference of the hose. Now, imagine that this hose is incredibly thin, so thin that you can't see its circumference without a magnifying glass. From far away, it would still look like a line, but the second dimension would still be there, curled up and hidden from view. String theory proposes that the fundamental building blocks of the universe aren't point-like particles, but tiny, vibrating strings. These strings are so small that they are far beyond the reach of our most powerful microscopes. In fact, they're thought to be about the Planck length, which is 1.6 times 10 to the minus 35th meters. That's a decimal point followed by 34 zeros and then a 1/6. Mind-bogglingly small indeed. Just as different vibrations of a violin string create different musical notes, different vibrations of these tiny strings create different particles, the quarks, leptons, and bosons that make up all matter and energy. But here's the rub. String theory only works mathematically if the universe has more than 3 spatial dimensions. In fact, most versions of string theory require 10 dimensions in total, 9 spatial dimensions, and 1 time dimension. Where are these extra dimensions? If they exist, why can't we see them? The answer, according to string theory, is that these extra dimensions are curled up at incredibly small scales, far too small for us to detect directly. They are like the circumference of that garden hose, hidden from our view but still influencing the properties of the universe. What would Leonardo da Vinci think about the hidden dimensions if he lived now? But what does this have to do with the question of the universe's infinity? Could the existence of extra dimensions change our understanding of what lies beyond the horizon? Some physicists believe that the answer is yes. They suggest that the extra dimensions could provide a shortcut through spacetime, a way to travel vast distances without actually traversing all the intervening space. Imagine folding a piece of paper in half. 2 points that were once far apart can now be brought close together by folding the paper. Similarly, the extra dimensions could allow us to fold spacetime, creating wormholes or shortcuts that connect distant regions of the universe. What if we could use the fold to travel great distances? These wormholes, if they exist, could be a way to circumvent the limitations imposed by the speed of light, allowing us to travel to other galaxies or even to other universes in a relatively short amount of time. They are a staple of science fiction, but could they become a reality? Of course, the existence of wormholes is still highly speculative. No one has ever found any evidence of their existence, and there are many theoretical challenges to overcome before we could even consider building one. But the possibility remains. A tantalizing glimpse of a way to break free from the constraints of our 3-dimensional world and explore the vastness of the cosmos. But the extra dimensions could also affect the shape of the universe itself. They could allow for more complex topologies, more intricate ways for space to curve and connect. Perhaps our universe is not simply flat, open, or closed, but something far more exotic. A multi-dimensional tapestry woven from space, time, and hidden dimensions. What if the fabric of reality is far more elaborate than we have imagined? These ideas may sound strange and abstract, but they have the potential to revolutionize our understanding of the universe. If string theory is correct, it would mean that our reality is far more complex and interconnected than we ever thought possible. It would mean that there are hidden dimensions all around us shaping the very fabric of space-time. It would also mean that what lies beyond the horizon may not be just more of the same, but something fundamentally different, something that we can't even begin to imagine. Perhaps beyond the horizon lies access to other dimensions, with an unlimited possibilities, a potential portal of science and knowledge. New mathematical equations could allow us to solve these secrets. It's not just about distance anymore. It's about accessing a whole new realm of existence. What if our quest for infinity has been focused on the wrong dimensions all along? Even as we peer through the lens of string theory, catching glimpses of dimensions beyond our own, a fundamental truth remains. Cosmology is a science built on unanswered questions. Progress is not about arriving at a final destination with all of the mysteries finally explained, but rather the act of defining the newest, most interesting puzzles. This may be more important than getting all the answers. We've charted a course through the observable universe, but the map is still incomplete. The shoreline is far out of sight, and in its place we have a horizon of the unknown. What are the next big questions that will drive cosmic exploration for decades to come? What future missions might provide those elusive answers? Consider dark matter and dark energy. These two cosmic enigmas comprise about 95% of the universe's content, yet we know virtually nothing about their true nature. It is a cosmic irony of epic proportions. We know more about the surface of the moon than we do about the dominant constituents of the universe. What exactly is dark matter? Is it composed of weakly interacting massive particles, axions, or some other exotic particle that we have yet to detect? Perhaps it doesn't exist in particle form at all. What if dark matter is a consequence of modified gravity, a deviation from Einstein's theory of general relativity on the largest scales? And what about dark energy? Is it a cosmological constant, an inherent property of space itself? Or is it a dynamic energy field, constantly evolving and interacting with other components of the universe? Perhaps dark energy is not even real, but an illusion created by our incomplete understanding of gravity. Astronomers are currently using a combination of space and ground-based telescopes to map the distribution of galaxies and measure the expansion rate of the universe with unprecedented precision. These surveys will provide valuable clues about the nature of dark matter and dark energy, but they may also reveal something entirely unexpected. Imagine a fleet of next-generation telescopes orbiting the Earth and the Sun equipped with advanced sensors and sophisticated instrumentation. These telescopes are not just collecting data, they are actively searching for answers, for anomalies in the cosmic microwave background, for subtle distortions in the fabric of space-time, for any hint that might challenge our current understanding of the universe. One such mission is the European Space Agency's Euclid telescope, which launched in 2023. Euclid is designed to map the distribution of galaxies over a large portion of the sky, providing unprecedented insights into the nature of dark matter and dark energy. Another promising mission is the Nancy Grace Roman Space Telescope, formerly known as WFIRST, which is scheduled to launch in the mid-2020s. Roman will have a wide field of view, allowing it to survey large areas of the sky quickly and efficiently, searching for distant supernovas, gravitational lenses, and other cosmic phenomena. But the quest to understand the universe is not just about building bigger and better telescopes. It's also about developing new theoretical frameworks, new mathematical models, and new ways of thinking about the cosmos. Physicists are currently exploring a wide range of theoretical ideas, from modified gravity theories to extra-dimensional models to quantum gravity approaches. These theories are often complex and abstract, but they offer the potential to revolutionize our understanding of the universe, to provide answers to questions that we haven't even thought to ask yet. Perhaps the most fundamental question of all is this: what is the origin of the universe? What happened before the Big Bang? Did the universe emerge from nothing, or was it preceded by something else? These are questions that push the boundaries of science, questions that may never be fully answered. Some physicists propose that the Big Bang was not the beginning of everything, but rather a transition point in an eternal cycle of expansion and contraction. They ask if there was a universe that came before ours. Others suggest that our universe is just one bubble in a vast multiverse, an infinite collection of universes, each with its own set of physical laws. These are just a few of the many unanswered questions that continue to drive cosmological research. Science thrives on the questions that we cannot yet answer, on the mysteries that beckon us to explore, to discover, and to understand. The quest to unravel the secrets of the universe is a journey without end, a journey that will continue to challenge us, to inspire us, and to push the boundaries of human knowledge for generations to come. Even as we stand on the shoulders of giants, armed with equations and instruments that would have been unimaginable to our ancestors, we have to recognize the limitations of all our knowledge. We search through it all: dark energy, wormholes, New physics. One fact will be there forever. We are still just creatures on a planet orbiting a normal star in a normal galaxy. We're finite beings attempting to grasp the infinite. Does that make the quest pointless? Absolutely not. Think about the earliest humans gazing up at the night sky. They saw patterns, told stories, and imbued the stars with meaning, all without the slightest understanding of what those pinpricks of light actually were. They lacked our telescopes, our mathematical models, our understanding of astrophysics. Yet they felt the same sense of awe, the same primal curiosity that drives us today. Centuries later, Galileo Galilei pointed his telescope towards the heavens, revolutionizing our understanding of the cosmos. He saw mountains on the moon, moons orbiting Jupiter, and a universe far more complex and dynamic than anyone had previously imagined. Imagine the wonder he must have felt, peering through that crude instrument, catching his first glimpse of a universe teeming with new and unknown wonders. Today, we have access to knowledge and technology that Galileo could only dream of. We can detect gravitational waves from colliding black holes billions of light years away, map the distribution of galaxies across vast stretches of space, and even glimpse the afterglow of the Big Bang. Yet the more we learn, the more we realize how much we don't know. The universe remains a vast and mysterious place, filled with unanswered questions and tantalizing possibilities. But what does it mean to be a sentient species capable of asking these ultimate questions? What is it about us that compels us to explore, to discover, to push the boundaries of human knowledge? Is it simply a biological imperative, a survival mechanism that drives us to understand our environment? Or is it something more, something deeper, something that speaks to the very essence of what it means to be human? Perhaps it's a combination of both. We are, after all, products of evolution, shaped by millions of years of natural selection. Our brains are wired to seek out patterns, to make predictions, and to understand the world around us. This innate curiosity, this desire to know, has been essential to our survival as a species. But there's also something more to it than that. We're not just trying to survive, we're also trying to understand our place in the universe. We want to know where we came from, why we're here, and what our ultimate destiny is. These are not just scientific questions. They are also philosophical and spiritual questions, questions that have been pondered by philosophers, theologians, and artists for centuries. Think about the works of William Shakespeare, the music of Ludwig van Beethoven, the paintings of Vincent van Gogh. These are all expressions of the human spirit, attempts to grapple with the big questions of life, death, and the universe. They are testaments to our capacity for creativity, imagination, and wonder. And that, perhaps, is what it means to be a sentient species capable of asking these ultimate questions. It means that we have the capacity to not only understand the universe, but also to appreciate its beauty, its mystery, and its awe-inspiring scale. It means that we are not just passive observers, but active participants in the cosmic drama, striving to unravel the secrets of the universe and to find our place within it. Maybe you are asking now if what we are doing is important for our species to survive. Is this knowledge relevant? Does having more data help us as a species? The only answer is that all knowledge is valuable. We strive to know everything. We are human, and we wish to know. And so, the quest to understand our origins and the universe's boundaries is not just a scientific endeavor, it's a human endeavor, a reflection of our deepest hopes, fears, and aspirations. Whether the universe is finite or infinite, its scale dwarfs human comprehension, but it does not dwarf human curiosity and wonder. Our cosmic address may be a tiny one, but we are, at least for now, the universe made aware of itself, finite beings contemplating infinite possibilities, an incredible circumstance.